A question I get all the time: Roman, what is the best way to learn to code for quantitative finance? My answer has largely been the same for years, and that is to build projects. This is not about padding your resume. This is not about padding your GitHub profile. This is about learning to engineer solutions to problems from scratch. In the old days, we used to go to Stack Overflow. We didn't ask ChatGPT or Gemini to generate a code snippet for us. In fact, if we have any hope to actually build trading systems, trading models, backtesting engines, do we really want these LLMs to write all of the code for us? Certainly not. We need to be able to build these systems ourselves, but we all have to start somewhere. So what I'm going to do in this video is I'm going to walk you through from A to Z how to build an implied volatility trading dashboard. This is a trading tool to help identify potential edge in volatility trades. I'm going to show you how the tool works, and then we're going to walk through the build from scratch. Everything you need for this project will be made available in the description below. I will post the source code on the Quant Guild library on GitHub. So if you would just like to access this tool and use it, you can feel free to do so. Moreover, if you're working through the build from scratch and you get stuck or something breaks and you need access to the source code, you can check it out there. So I'll post that link in the description below. I'll also post a link to Interactive Brokers. That's how we're going to be accessing the market data required for this trading dashboard. I've been trading with Interactive Brokers for nearly 10 years. They're the only broker that I trade with in an algorithmic capacity. Highly recommend them. Check out the link in the description below to go ahead and create an account that we can use for this implied volatility trading dashboard. Lastly, as I get started demonstrating how this implied volatility trading dashboard works, if you want to support the channel so I can continue to make videos just like this one, and if you would like to master your quantitative skills, check out quantguild.com. All right, so how do we go about using this implied volatility trading dashboard? Well, if you haven't seen my video on how to trade option implied volatility, then please check that out first. It is the perfect precursor to developing this app. If you're ready to get started, then what we're going to first do is connect to Interactive Brokers Trader Workstation. When we get to the point in the build where we configure a host and port, then I will show you how to do that. But for now, bear with me. We're just going to go ahead and connect. You can see in the logs we've successfully connected. And now what we're going to do is pick a ticker that we want to analyze the implied volatility data of. So I'm going to pick, in this case, let's use NVIDIA. We're going to look back 2 years and query this implied volatility data. Okay, so now I have this current implied volatility. I'm scaling it by the square root of 252 to annualize it. I have this vol range and just a brief analysis of the current regime. Okay, cool. Now let's click this Analyze Implied Volatility button, and we get all of these crazy looking charts. Now, if you watch the video, How to Create Option Implied Volatility, all of these charts will be very familiar to you because what we're doing is running the regressions from that video. We are looking at the current implied volatility relative to the average implied volatility for the next 30 days. So what we're doing is we're regressing the forward implied volatility on the current implied volatility. And we're plotting the regression line against y equals x to see what the effect is on the current to forward basis. Now remember, all of trading is about finding a statistical basis for your decision making. That is effectively what we are trying to do here within this dashboard. We're trying to see if, given the current state of implied volatility, there's some sort of statistical basis for a trade that's either long vol or short vol. Let's take a look in the case of NVIDIA. So here I have this regression on the current implied volatility relative to the forward implied volatility for the past 2 years. This dotted line is y equals x. This red line is the regression line. You can see the slope of the regression line is less than 1. What that means is implied volatility tends to be what? Past this intersection, lower than the input. For example, if we input 0.7, we get something around 0.52. This y equals x line is where 0.7 as an input would yield 0.7 as an output. Okay, well maybe there's a statistical basis for a trade there. Maybe if implied volatility is 0.7, we should go short vol. Maybe. Okay, what about the left side of this intersection? Well, relative to y equals x, if I plug in, let's say 0.4, the regression line predicts 0.4, what's that, 0.42? Something like that. It's higher than y equals x, so maybe I want to go long vol there. This isn't a perfect system. A lot of assumptions are being made. Transaction costs, delta hedging, the position cost itself can eat away at any potential profits. What we're doing is we're creating this as a starting point. Now, what else can we do? Well, what if I split up this regression into two separate regressions? So this intersection point with y equals x here, I'm going to create two buckets. I'm going to call it a high volatility regime and a low volatility regime. Low is going to be in blue, high is going to be in red. Now, running a regression in these two separate situations will allow us to isolate this effect that low volatility may imply higher volatility going forward, and high volatility may imply lower volatility going forward. Again, sometimes this effect is flipped. Sometimes all of the transaction costs and hedging costs, etc., eat away at your profit, but this is a place to start. Okay, so that's what this chart is showing us here. What we're doing here is we're not just looking at the current implied volatility relative to the forward implied volatility. We're looking at the difference. So if the difference is positive, that means that future volatility is actually higher. If the difference is negative, that means future volatility is lower. And what you can see is in the high volatility regime, it's all negative. And in the low volatility regime, it's all positive. So it's a very interesting effect to observe. So essentially, on average, in this low volatility regime, forward volatility tends to be higher. In this high volatility regime, forward volatility tends to be lower. Now, is there a way to measure how profound this effect is? There certainly is. Now, there's not enough time to talk about least squares, not enough time to talk about how everything functions, how explained variation works, the entire idea behind it itself. But what we can do is look at something called the R-squared value. Essentially, the higher the R-squared value, the more profound this effect. So in a low vol regime, we have an R-squared of 0.057. Now, this is out of 1. So this explains very little variation in the forward vol based on the current vol. But with the high vol regime, we get an R-squared of 0.387. That's significantly higher than the low volatility regime. So maybe there's a statistical basis for us to trade in that capacity, going short vol when the implied volatility is high enough. Now, the current implied volatility is what? 0.44, 44.05%? There's no trade here. There's no trade. In fact, we're very, very close to this regime split. This regime split is not a stationary value. As time marches on, heck, even if I change this window, this value is going to change. So we have to keep this in mind. Everything is time variant here. It's changing over time. Nothing is converging. Nothing is static. We're doing our best to create a model to find some sort of edge. All right. Well, I've also plotted the time series of implied volatility, the current level, the mean across this time series, and the 75th and 25th percentile. And here you can see that volatility relative to historic volatility has been pretty low recently. We had this little spike here, and now we're kind of between the 25th percentile and the mean. This could mean a variety of different things. So maybe we think that volatility will increase. It's been low for a while, but again, based on the current level and this regression, it doesn't necessarily suggest that effect. So This is what I'm teasing out with this trading dashboard. So this is how we can go about analyzing some sort of potential for trading volatility on a particular equity. In this case, this is NVIDIA. You could use it on an ETF or really any symbol. But this is how you would go about interpreting the dashboard. Time to start building. We don't need no ChatGPT or Gemini for this. We're going to build it from scratch. So let's start with a brand new workspace, brand new Python file. I'm going to call this, let's say, dashboard.py. And look at this, right off the bat, we get generate code. We don't need no code generation. We're here to write code from scratch. All right, we're going to start with our imports. We're going to need to import quite a few things. Import tkinter as tk. We're going to use tkinter to build the frame of our application. We're going to need some other items in tkinter. We're going to need ttk message box and scrolled text. So import from tkinter, import ttk, message box, and scrolled text. We also need to import threading. We're going to import time. For the implied volatility data, we're going to use pandas. So import pandas as PD. We're going to use matplotlib to visualize the regressions. We also need the figure canvas so that we can use it with tkinter. Now we also need the interactive brokers Python API. This is going to be IB API. So from IB API dot client, we need eClient. From IB API dot wrapper, we need eWrapper. We also need the contract class so that we can get the data for a particular symbol. And we need date time to format dates correctly. And we can also import warnings, and we can filter warnings. All right. If any of this doesn't work, run this. If any of this doesn't work and you get some sort of error, module not found, whatever it may be, then you likely need to run a pip install on that package. So if you don't have pandas, you don't have matplotlib, you don't have IB API, what you need to do is open up a terminal. Assuming you've installed Python correctly on Windows and you have the Python package manager added to your path, then you're going to be able to run a pip install on these packages. So I would say pip 3 install pandas, for example, if I was missing the pandas module, or pip install pandas if you're not working with that particular version of Python. It'll be pip or pip 3. And you would need to do this for every module that you do not have. Okay. Now that we've gone about importing everything that we need, we're going to create a class to manage the connection and data from interactive brokers. We're going to call this the IB app class. And this is going to be an implementation of the eClient and the eWrapper from the IB API. Look at this. It's auto finishing for me. Goodness gracious. Get this AI out of here. All right. So we've created this class. Now what we're going to do is we're going to create the constructor. We're going to initialize eWrapper and eClient in this particular class as itself. And then we're going to add fields for the connection and the historic data that's being queried from the creator workstation. So def init self, this is the constructor for the class. I'm going to say eClient. We're going to initialize it with self and self. So we're operating with this as the eWrapper and eClient implementation. And then we are going to have a field for connected. We're going to set it equal to false by default. Then we're going to have a field for the historical data, and this is going to be a dictionary. So we created this class and it's implementing eWrapper and eClient, but what does that actually mean? Well, we're going to establish a connection to the creator workstation to interactive brokers, and we're going to make a data request, and that data request has to go somewhere. it's going to go to this class. That's the purpose of this class. Now, sometimes there's going to be errors. So we need to be able to log this to our terminal. So I'll say def error. We're going to take self rec ID, error code, error string, and we are just going to print this out to the console. So I'm just going to use a formatted print statement, and we can just go ahead and print all of these values. So we're going to print the rec ID. We are going to print the error code, and we are going to print the error string. Okay. Turned off the AI autocomplete, so everything will be nice and peaceful here. All right. Now we need to create some sort of function to be able to get historic data and manage historic data. What does this look like? Well, we need to create a function called historical data. And this is where Interactive Brokers is going to send the historic data for implied volatility when we request it. So we're going to create a request. It's going to have a request ID. It's going to go to Interactive Brokers, and it's going to come back to this class. It's going to give us the bar data and the request ID that's telling us which implied volatility we are essentially asking for, and it's going to store it in this historic data dictionary. Okay. If the request ID is not in self.historical data, then that means we have not queried any particular request for this request ID. So we are going to set the historical data dictionary to have this rec ID with an empty list. Because remember, this dictionary doesn't have a default value for each key. So we're going to create a request, call it request, let's say 1. And the server is going to get this request. It's going to respond, hey, request 1, and here's your data. But we need to be able to put that data somewhere. So what we're saying is historical data, take that request ID 1, and take all the data. We're going to throw it into this empty list. So what we'll do is we'll say self.historical data. Now that we have this empty list, using this rec ID, we are going to put all of this data in. So we're going to put date bar dot date. We will put open bar dot open. We will put close bar dot close. We will put low. We'll put high bar dot high. We'll put low bar dot low, and we'll even have the volume. All right. So we're appending a dictionary to this list that we've created for this specific rec ID. All right, so we're going to create some sort of implied volatility request to Interactive Brokers, call it rec ID 1. It's going to respond with all this data. So what we're going to say is, hey, for rec ID 1, let's create an empty list. And within this empty list, let's create a dictionary that's going to have all of this data. All right, and then once we're done fetching this historic data, we want a message to ensure that we know that it is done. So historical data, this is going to be within the class, not within that function. Historical data end, and looks like this auto finished for me, but we need rec ID, start, end, and we don't need to return anything. Really, we just want to print historical data has been received. For rec ID, and then we'll put in the rec ID. Okay. All right, so this is going to be the class that's going to handle the callback from Trader Workstation with our historic data. Great, and then we're going to use that data for our regressions. Now's the fun part. We got to build the user interface. How are we going to do this? Well, we're going to create a class. Implied Volatility Dashboard. And in the constructor, I am going to pass the root of the user interface. Now, whenever I create a TK enter sort of app interface, I need to create some sort of root of that application. You can think of this as like the frame. And that root, that frame, is where I'm going to add all of these elements. So within the constructor here, I'm going to assign a field within the Implied Volatility Dashboard class this root value, this root object. So anytime I want to add something to it, I can just call self.root. So self.root is equal to root. Now, anytime I want to add something to this frame, I can just call self.root. So self.root.title, this is going to be the Implied Volatility Trading Dashboard. And that's accomplished because I have this self.root equals root here. So anytime I want to add or change something to this app, this frame, whatever you want to call it, I can just call self.root. So I'll call self.root.geometry, and this is going to be the default application size. I'll make it 1400 by 1200. There's a lot going on. You can play around with the size if you'd like. Now we need something for the data, so I'll call it self.optionData. This is equal to none for now. Self.VolatilityData, this will also be equal to none. Self.current implied vol, this is equal to none. These are just going to be placeholders for when we actually want to replace it with data we query from Interactive Brokers, the server. We're going to need to handle the connection to the server. So we need an instance of the IB app that we created here. So I will say self.IBApp is equal to IB app. And anytime I want to handle the historic data, right, I make a request to the server, I'm going to be able to find it in this IB app field within this class. Pretty handy. Moreover, I need a field to tell us if we are connected or not. And I'm going to also set a default vol annualization to be 252. And you can change this depending on if you're going to be querying, let's say, daily implied volatility or weekly, monthly, however you are going to be managing the bar size. So if you need to change this to, say, be 52, if you're using weekly or however you want to do it. So this is the annualization. This is how we're going to be scaling the implied volatility. Then we're going to need to create a function to set up everything in the UI. So this is going to be all the buttons, all of the charts and whatnot. And that's going to be just about it for the constructor. All right, what do we need now? We need a couple of different helper functions. So for starters, we need to create a function to create an equity contract. So this could be some sort of equity like we used NVIDIA as an example in the start of this video. But here, this could also be for an ETF like SPY. So we'll call it create equity contract. We will take a symbol as an input, and that's going to be that field in the app that we saw. And we'll say contract is equal to an empty contract object. This is imported from the Interactive Brokers API. Then I'll say contract.symbol is equal to symbol.upper. Okay, because this is how we need to format the symbol for the contract that we're sending to the server to request information from. It needs to be all capital. So in case the user enters it in lowercase or whatever, we'll get it to capital. And then the security type is going to be stock. The exchange we will say is smart. And the currency we will just default to US dollars. Then we'll return the contract. So this is how we're going to go about building the contract. Okay, so essentially that button is clicked when we enter the symbol, and this is what we're going to create based on whatever is entered. We're going to create this contract object so Interactive Brokers knows what data to send back to us. Now it's time for the beast. Now it's time for the beast. We need to create this setup UI function. All right, buckle up here. This is the fun part. So def setup UI self. the function to set up all of the components on the frame. All right. We already know if we want to add things to this frame, we can just use self.root. So we need to first create this frame. Main frame is equal to ttk.frame self.root. We'll have some padding for the items within the frame. I'll just create it. Start with 10. You can alter that if you want more padding. The frame is also going to have a grid layout. So row is equal to 0. Column is equal to 0. And then we'll say sticky, and we will have west, east, north, and south. Okay. Sticky is equal to this tuple. Perfect. All right. Let's start by configuring these widgets now. All right. Self.root.column.config 0 weight 1. Self.root.row.config 0 weight 1. Mainframe.column figure, we will have 1 weight 1, and then mainframe row configure, we will have, let's say, 5 weight 1. All right, we need a connection frame. All right, so essentially these are just going to be the weights of the grid, all right, that we are establishing in the main frame. Now we need to create each little frame for each section of the application. So if you remember, we had the connection frame, then we had the frame where we can query the historic data. So I will say conFrame is equal to ttk.labelFrame, main frame. This will be the interactive brokers connection. And we'll throw some padding on there too. Just call it 5. And then this will be in row 0, column 0 with a column span of 2. So for this particular frame, we'll say conFrame.grid, throw it in row equals 0, column is equal to 0, column span is equal to 2, sticky, we will put TK west and TK east, and then pad Y will do 0 and 10. So there will be some padding vertically. All right. Now we're going to add some labels and some inputs so that we can manage this connection. So this conFrame is just a section in our window where we're going to be putting items to manage this connection to the creator workstation. So I'm going to have this ttk.label, and this is going to be in the conFrame section, which is the connection frame. This is going to be the host for the application, and we'll throw this in row 0, column 0, and we'll give it some padding on the x axis. So pad x is equal to 0, 5. The host var is actually going to be a string var, and this is going to be the value assigned to the input text field. So whenever it changes, this is how we're going to get that information from the user interface. We're not just going to fetch it from the input object. It's better practice to create a variable, a dedicated variable for this value, and access it via that dedicated variable. So that's what this self.host var is. It's going to be a string var with a value of the host, which defaults to 127.0.0.1, no place like home, localhost. A fun a fun programming connection joke for you guys. All right. This is going to be, again, an entry. So this is the variable that's going to house the data for this host field, but we haven't created the host field yet. So that's an entry. That's this input form. And we're throwing this entry in the connection frame. And it's going to have a text variable value of self.hostVar. This is what connects the input to a variable. And in this case, the variable is hostVar. We'll say the width of this input will be 15, and then we're going to put this in column 1, row 0. Okay, so row is equal to 0, column is equal to 1, and we'll give it some padding on the x 0, comma 10. Okay, maybe I will expand this a little so you guys can see if you have to. Yeah, that's better. We don't need the file tree open. Okay, cool. So that's going to be the host. Now we're going to do the same thing for the port. All right, and this is pretty much just rinse and repeat. So I'm actually just going to copy and paste this block. And Shift Tab will reverse tab it in if you didn't know that. So instead of host, I'm going to do port. And I'm going to put this in column 2. Okay, so 0, column 1, column 2. And I'm going to keep the same padding. The default here is going to be 7497 for paper trading. The host var in this case is going to be now the port var because we're dealing with the port. So port 7497 is the default port for paper trading. This is going to be our string var. We need to change this entry to have the port var default. The same width, probably fine. We can do a little bit less, I guess, because the port is shorter than the host. And it's not row 0, column 1. It should be row 0, column 3. Cool. And then we're going to add some buttons so that we can actually make this connection request. Self.connect button is equal to ttk.button. And we will do the con frame and text is equal to connect. The command is going to be equal to self.connect IB. And we're going to have to create that function to run this connection request based on the host and the port that are entered into those text fields. We can also add, well, I guess we have to add this to the grid. So self.connectButton.grid, we'll throw this in row 0, column 4. So this is beyond the port item, the port input. And then we'll also add some padding on the X. We'll make it 0 and 10. Okay. And we can just copy and paste this too. And we can do the same thing for disconnect. So we'll have disconnect. Instead of connect IB, we should call this disconnect IB. And we can just leave this as disabled for now. State is equal to disabled. And then it's not in column 4, it's in column 5. And then it's not called connect button, it's got to be called disconnect button. Okay. So we've now created the entire frame for the connection within the main frame of our application. That is exactly what we've done up until this point. We created this connection frame, this mini frame within our application. We said there's a host label, a host input, a port label, a port input, and a connection button, disconnection button with commands that we've yet to build. And this is sufficient for the connection section. So the next section of this is to build out the query frame, the data query frame. And it's pretty much the same process. So I need to create a new frame now. I'm going to call this the data frame. Not to be confused with the pandas data frame. This is just going to be the frame within the bigger application where we're going to be querying the data. So we'll call this ttk.labelFrame. We'll put this in the main frame. Remember, we have this main frame, we have this connection mini frame, and now we have this data query mini frame. And the text will be data query. Throw a little padding on there. Everything should look nice. We're going to put this in row 1 now. So we have that first connection frame. We'll throw this in the next row. We'll call this column 0 with a column span of 2. We'll call this sticky as well to west and east. And then we'll throw some padding on the y-axis. As you go through this, if there's anything you want to change with the padding or text fields, you're free to do so. That won't change the core functionality of the application that we're after. Now we're going to create the exact same thing that we did here with the host and port, but this time for the symbol and the look back period, the duration for the data request. What I would do is I would just copy this. So copy these three things again, and we'll just change everything down here. So Shift Tab brings it in. We have port. Okay, instead of port, we're working with symbol here. Okay, it's not in the connection frame. It should be in the data frame. Again, this is the frame where we're going to be querying the data from, not a pandas data frame. All right, we're going to throw this in column 0. Okay, we're going to keep the padding. The default value, it's not going to be port var. It's going to be symbol var. Symbol var. And the value, we can just default to SPY. You can make this Apple, NVIDIA, whatever you want to do. And the entry is going to be in the data frame. And remember, the string var is going to be symbol var. And we will put this in column 1. The exact same thing for duration now. Cool. And we will call this duration. You could call this look back if you want, or whatever else to imply that we're querying data back that duration. I'm just going to call it duration, and we're going to keep this in row 0, column 2, and the default will be 2 years. So Interactive Brokers has specific format for how it specifies date ranges. So 2 space Y is how it does 2 years. You can look for other ranges as well in their API documentation, or you could ask your favorite LLM if you would like. Symbol var is going to be now duration var, and we are going to make this duration var instead of symbol var, and this will be in column now 3. So we have column 0, column 1, column 2, and this will be in column 3. Cool. Now we need to add a button to actually query this stuff and analyze the volatility. So I'm just going to copy the connection and disconnection buttons, and I'm going to change everything here so that it is correct. Instead of connection, what do I have? I have a query. So this will be query button. This will be query button. Instead of connect frame, we're not throwing this in the connection frame, right? This is going to be in the data frame, where we're going to be querying this data from. Instead of connect, this will be what? Query IV data. So now we need to create a what? A command to, you guessed it, query the data. And of course, this should probably be disabled before there is a connection to Interactive Brokers. Okay. This will be in, column 4 is totally fine. So that actually lines up with the original connection frame from the connection button. So column 4 is totally cool. Then for this disconnect button, we need to replace this with analyze button. And instead of connection frame, it will be data frame. Instead of the text being disconnect, it will be analyze the implied vol. And we'll leave this as disconnected too until there's a connection. And instead of disconnect IB, this will be analyze volatility. Okay, and then this will be the analyze button dot grid. We'll throw that in column 5, and we will be all set. That will be completely sufficient for this data portion of the application. So far we have our frame, we have our connection section, we have our query data section, our data query frame, and we're going to continue building this out to the section that we're going to populate with data now. So this is pretty much rinse and repeat now. We got to create this vol frame. So we have this label frame. We're going to throw it in the main frame. This is going to be the current implied volatility. Throw some padding on it. Okay, the grid will be row 2 now. So we had row 0 connection, row 1 the query panel, and now this is going to be the data. Throw it in row 2, column 0, column span 2, again sticky west and east, and we'll throw some padding on for good measure. We'll make it padding Y, and we'll just add labels now for the current implied volatility. Then we can also add some other information as necessary. So let's start with this label for current implied volatility. We'll say ttk.label. We'll throw it in the vol frame. We'll say the text is equal to current IV, and we will of course populate this as we get data. We'll throw this in row 0, column 0, just like we did with the other fields when we first created this section. Self.currentVol label. We will say ttk.label, throw this in the vol frame, and the text will be not available for now until we get data, and the font will be, we'll just call it Arial 12. We'll throw it in bold. Okay. The label itself will live in row 0, column 1. Okay, so we have the current vol label. We'll throw this in row 0, column 1, and we'll have a little bit of padding on the X. Perfect. And now it's pretty much just going to be rinse and repeat again. We did this for the implied volatility, so this is the vol frame. What else do we need? We need the actual computation. I suppose we could throw that in there too. So I'm just going to copy this guy, and we can paste it in just like we did before. And we will just make this instead. This will be now 0, 1, 2. This is column 2. And instead of current IV, this is just going to be the computation. And for the text, we'll just throw no data until we get data. This doesn't have to be bold. We can make this smaller. We'll just make this Arial 10. Column 3. So we're counting up here, right? 0, 1, 2, 3. This is going to be the label. This is the label. This is the label. And we're going to populate the next item with data when we get it from the server. We're going to do this for the volatility range too. So I'll just copy this again. Do this exact same thing. So I will call this then vol range. And this will be now in column 4. And then this will be in vol frame. We can populate this with NA till we get data. Arial 10 is fine, and then the actual data can live in, we can call this column 5. We probably don't need any padding on the X here. In fact, for the computation itself, we need less, so maybe like 10 is sufficient, because it's not, this is 12 bold. This is 10, so it's probably fine. All right. We need to keep going here with the volatility statistics and stuff. This is where we're going to be showing all of the information from the data that we queried. So I'll create another section here. And instead of vol range, this is going to be, well, I guess we need a separate panel for this. So I will create a new frame. I'll call this regime frame, and I will call this ttk.label frame. We'll throw this again in the main frame. This will be the volatility regime analysis. So this is just some systematic, like automatic way to process the data that has been queried. So it's not perfect, just like I said when we're using this trading app. We're not going to be clinging to these values as if they're perfect. Everything's time variant, nothing converges. But here, we're going to just have some conditional statements for proposing if it's, hey, this might be mean reverting, there might be a mean reversion signal, so on and so forth. So we have this regime analysis section. We'll create a little bit of padding as we've been doing in each of these frames. And we will throw this beneath the now the volatility frame. So we have connection frame, we have query frame, we have volatility frame. Now we have a regime frame. So this will be regime frame. We'll throw this in. This is going to be, I suppose, row 3 now. And column 0. This is the exact same setup as the other frames. Same thing, sticky, west and east. Throw some padding on the Y, and we'll be all set with this frame. So now we have this regime frame that we're ready to populate, and now we can copy and paste all of these ranges. So I'll just instead use the regime frame here. We'll throw this in column 0 and column 1, and instead of current vol label, oh geez, I guess I got to change all of those variables too. Goodness gracious. All right, so instead of, let's see, this should be vol computation and vol range label. So this should be vol range label. Good. And this should be vol computation label. Yeah. Okay. Good. And then this should be the regime label. And this should be the regime label. Good. And we're going to make this, we'll give this some more padding. We'll give this like 0 to 20 because this is going to be bold. So we'll make this like Arial 12 again. We'll call this bold. And that should do it. So that is the, instead of vol range, this is going to be the current regime. All right, nice. So this is going to be the label for the current regime. This is the text that we will populate from data, and we will put this in the regime frame section. Good. So effectively what we have here is, this is the regime frame, and we're going to put all of the labels and buttons in there. This is the volatility frame, labels and buttons. This is the data query frame, labels and buttons, and this is going to be the connection frame. Nice. All right. Beyond this regime label, what else do we need? We need percentiles, we need things like that. So let's create another one. We will do, instead of current regime, this will be percentile. Percentile, we'll throw this in column 2 now. We're counting up. Good. Instead of regime label, this is going to be percentile label. And then we'll make this percentile label. Throw this in column 3. Good. This doesn't have to be bold. We can make this Arial 10. Don't have to make everything bold. And that's going to be the percentile. So 0, 1, 2, 3. Good. Now we can do some sort of mean reversion signal label. So this will be mean reversion signal. We'll throw this in now column 4. This will be in column 5. And instead of percentile label, this is going to be the reversion label. And we can just use this here. And we'll leave it as Arial 10 NA. So that should be everything we need for this frame. And now we can move over to the status frame, and then we can create a function to help log messages. So that should be sufficient. Now we can create the status frame. So status frame is equal to ttk.labelFrame. Throw this in the main frame. Text is going to be equal to status. and then we will throw some padding on it like we've been doing all along. And then we will throw this now in the, not static method, status frame. We'll throw this in the 4th row, column 0, sticky is equal to, and we'll do tk.west, tk.east, and that should do it for this. Oh, we gotta throw some padding on. So we'll do pad y is equal to 0, 10. Okay, and that is going to do it for the status frame. So now we have the connection. So we have the main frame, we have the connection frame, we have the data query frame, the volatility frame, the regime frame. Now the status frame. So 0, 1, 2, 3, 4. It's going to be 5 total frames so far within this main application. Let's finish adding the items to the status frame, and then we can create the frame for the plots, and then we should be done with the user interface for the most part, except for the helper functions. So let's do self.status text is equal to scroll text. Okay, dot scroll text, and we'll throw this within the status frame. This is essentially our log. The height is going to be 6. Don't want it to take up too much space. It's not uncommon to throw some sort of menu bar at the top and then have like a view console logs and have it pop up as a separate item. That's how I do it in most of my trading systems. But for this particular app, it's totally sufficient to have like a little window to ensure that your connection is working and to print out any analysis that you might want. So maybe as an exercise, if you'd like to create a menu bar, you can feel free to do so. But we'll just put this in its own little section, and we will say that this is going to be, so the status text itself is in row 0, column 0, and we will make it sticky to west and east. Now keep in mind, as you're building out this user interface, if items aren't showing up in your TK insert window, in your window, that means you're missing the layout. It doesn't know where to put it. So keep that in mind. You can create the item itself, but if you don't tell it where to go, then it's not going to put it anywhere. So just something to keep in mind as you're working through this. So now the actual frame itself, we'll just column config it, and we'll give it a weight of 1. And now we can just go about creating the plot frame, and this is where we will put all of our plots, ttk.label frame, and we'll throw this in the main frame. The text will be implied volatility analysis results, and we'll make some padding. We'll throw it on 5. Cool. Tell it where to go. This is going to be the 5th. Row 5th, row 5, row 5th is going to be the 5th row, and it's the 6th, essentially, label frame that we have. Column 0, column span 2, everything we've been doing up until this point. Call it west, east, north, and south. We'll give it a column configure a weight of 1 and a row configure weight of 1. Cool. Now we need to configure our subplots from matplotlib and throw them on the canvas. So we'll do self.fig. There will be axes. We have axis 1. That is where we will put the regression of the current current implied volatility and the forward implied volatility, not difference. So we're going to regress the forward implied volatility on the current implied volatility. Self.ax2, self.ax3. So ax2 will have the difference regression in each regime, and axis 3 will be the time series of implied volatility and the percentiles. This will be equal to plt.subplots 1 to 3, fig size. Again, you can do whatever you like here. I'm just going to do 18 by 6, pretty standard. We need the canvas itself. The canvas will be equal to, this is where we use the figure canvas, tk-enter self.fig. We're going to throw this then in the plot frame. This is how we connect the canvas to the tk-enter window itself. So we have the figure from matplotlib. We're connecting this to our label frame. That's our canvas. And then we're just going to say self.canvas.get tk widget. And we will throw this in what? We got to tell it where to live, right? So row 0, column 0, and we'll make it sticky to tk west, tk east, tk north, and tk south. And that is going to do it for our user interface. That certainly was a beast, but well worth it. Now is the fun part. We get to actually build these functions that do stuff, interacting with the server and our client. So let's do that. Start with this log message function. Get the boring one out of the way first. So we want to be able to print to our log, our console logs. So what we'll do is we'll say timestamp. We'll create a timestamp for the message datetime.now, and we will use this string format for time. We will have hour, and then we will have minute, and then we will have second. Cool. Then we're going to do self.statusText is going to be having something inserted into the scroll box. So we will say tk.end, we'll insert it at the end, and we will insert the message and the timestamp. So that will be the timestamp, and then we will give it a message and a new line. Now, this is a function that hasn't been called yet, right? This is where we are going to be calling this function, giving it text, getting a timestamp, and then pushing that to the console log. So keep that in mind. This is a function to be able to print to that console log. It's not going to be printing a specific message. Whenever we want to print to the console log, we will call this function. We want to see the end, and then we will update idle tasks. Okay, and this will allow us to essentially just update the items in the status text scroll text console log in our UI. All right, now we get to create the connection to Interactive Brokers itself. So what we'll do is we will do def connect IB. Self, we will say we're going to try to connect self.hostvar.get. So the value of the host var is whatever we input into that text field. Remember, that text field is linked to the host var, so we will get that value and store it in this host variable. Same thing for the port var, portvar.get. Then we will log this message. We are trying to connecting to IB at host : port. Nice. Let's create a thread for this connection. We will try to create a thread for this connection. So we'll say self.ibapp.connect through the host import that we just got from our user interface. This will be master client ID 0. Okay, if you're running several instances of apps, if you're running several instances of apps on the same trader workstation, same network, this could be an issue, but for now, don't worry too much about it if you're not running a couple of different systems. I've had issues with this. I've run, a couple of different systems through the same instance of trader workstation, and you have to increment based on the connection. So something to keep in mind, but for now, if you're just running this, 0 is sufficient. Self.ibapp.run, and that is effectively what we are trying to do. Of course, we will accept any sort of exception as E. And what do we do with an exception? Well, we gotta log it. So we will log it. We get a connection error, and we will log it as E, whatever that is. Okay. Now we imported threading, so we will try to handle this connection as a thread. Threading.thread. We will say target is this function connect thread. and we will set daemon to true, and then we will start this thread. So we want to pass through this thread. We don't want to get stuck here in a linear capacity. We want to turn this function effectively on, try to start this connection, but allow the app to continue running. So let's try to wait for this connection now. So I will say for whatever in range, let's say 50, we can do if self.ib app.connected. So the only way that this would occur is if the server responded with, hey, we connected successfully. Well, if we connect successfully, we can break. We don't want to wait anymore. Otherwise, we will time.sleep 0.1. So this is going to sleep 5 seconds. So we're going to wait up to 5 seconds for a connection to be successfully filled from the server, from our client. So we hit connect. It's going to try to connect at this host and port. If it connects successfully, then this flag will be true at some point throughout the 5 seconds. We'll break this loop and we can continue on. Okay, so if we connect successfully, what do we want to do? Well, we had a whole bunch of buttons that we needed to enable, right? We want to be able to query data. We want to be able to maybe analyze volatility, disconnect. So we will say self.connected is equal to true. We will say self.connect button.config. We don't need to connect anymore, so we can set this to disabled. Then we can say self.disconnect button is going to be configured to what? Normal. We want to be able to disconnect now. Same thing for the query button. Now that we're connected, we can run a query. Button.config state is equal to normal. And then we want to log what? What happened? Well, we successfully connected to IBTWS. Terrific. Otherwise, what? Self.log message failed to connect to IBTWS. And this makes sense, right? Because if we went through this entire sleep, this 5-second sleep, then what? This will be false. So we will log that we failed the connection. Okay. If it breaks, then we know this is going to be triggered for sure, because the only way for this to break is if we have successfully connected. The only way to successfully connect is to have the server respond with a Boolean that suggests that we have connected successfully. Cool. Don't lose sight of this. That's why we have this up here. Our VSCode editor is telling us, remember, we have this connect IB function, and we're still operating within this try. So we need to close with an except. Okay, so I have except, and we're going to accept exception as E. And we got to keep that within the function. And we will say self.log message, and we will log that there is a connection error, and we will log that as E. Okay, and this needs to be tabbed in one more time so that it's in line with this try within the connect IB function. And that will do it for this connect IB function. What about disconnect? Disconnect, equally as important. Def disconnect IB self. We will say try. We will try to do IB app.disconnect. Where are these functions coming from? Well, we implemented the eWrapper and eClient from the Interactive Brokers API. These functions are coming from those classes. So we're going to try this disconnect. We'll set the connection to false. We'll want to be able to connect again. So we will configure the state of the connection button as normal. We want to be able to, well, I guess we don't want to be able to click disconnect, so we will set this to disabled. Self.query button.config state is equal to disabled. We don't have a connection, so we can't query, and we can't analyze any volatility. Cool. We will not display any implied volatility then. So we will just set the current implied vol to none. And we will update the current vol display. And we will just leave it blank. And then we will log to the console. Disconnected from IBTWS. Of course, if there's some sort of error, we will accept an exception as E, and this will be self.log message F disconnect error, and we will leave that as E. So now we have our connect and disconnect functions with appropriate logging. Now we get to create the function to actually query data. So we'll call this query data. And we will say if not self.connected. We can't go about querying data if we don't have a connection to a data provider. So we will say message box show error not connected to IBTWS. Okay, so we need that connection. Otherwise, we need to get the symbol from the symbol var. And we need to make this uppercase. And we need to get the duration from the duration var. And this is exactly what we did above with the host and the port. So we have these variables tied to the input fields, and we can just get those string vars relative to the actual input. And we do that by just accessing the string vars directly with these getters. Okay. We're going to try to query the implied volatility now. So I'm going to log that we're trying to query it. Log message querying implied volatility for, and we'll throw the symbol. Dot, dot, dot. Okay. Now we are going to clear the historical data, if any exists. And we are going to try to run this query. Okay. Remember, the historical data variable is a dictionary. The dictionary has a key that is the request ID for the data that we are trying to access. So if I'm trying to query NVIDIA data, that request ID might be 1. Okay. Then if I'm trying to query Apple data after, that request ID might be 2. So this dictionary is keeping track of the data based on that request ID as a key. And the list that it returns is going to be a list of a dictionary that contains all of the information from the query. All right. We need to establish the contract, but fortunately we already created a function for that. So the contract is equal to what? Self.create equity contract, and we'll throw the symbol in there. Now we can actually go about making the historical data request. Self.ib app.rec historical data. We're going to have rec ID 1. Contract is equal to the contract that we just created. Then we will say end date time is blank. We want as current as possible. The duration string is going to be the duration, remember, from our app. That's what we did here with the duration var. Then we need to do the bar size setting. And I'm going to use 1 day. You can use whatever you like. You can change how vol is annualized. But we're going to use 1 day. What to show? Well, this is a volatility trading dashboard. We want option, implied, volatility. Okay. We want to use RTH, format date. Keep up to date. We don't need this to be up to date. And we can just pass an empty list for the chart options. And that is sufficient for this historical data request. All right. We can add a timeout for the fetching of this data if it doesn't get returned in a timely manner or something is wrong, we could say timeout is equal to, say, 15. Start time is equal to time.time. And then we can wait for this historical data. So while one not in self.ib app.historical data, that means that we haven't received the data to that key yet. So we haven't received the data. And while time is still before the timeout time, so it's less than the timeout time, all right, then we are just going to wait. And this is just us waiting for the server to return the historic implied volatility data to us. Here we go. What happens if we get data from the server? If one is in self.ib app.historical data, well, data is equal to self.ib app.historical data. And where can we find it? Well, the key for the rec ID is going to be 1. That was the request ID we used here, right? So if the length of the data is greater than 0, that means we got something. So we could say self dot, I'll call it equity data, I guess. I mean, I don't want to be confusing. Well, I guess this will be a data frame, so I can make it implied volatility. Self.equity data is equal to pd.data frame data, and then we'll have date and implied volatility. So we'll say self.equity data, and we'll throw date in there. We'll set this equal to pd.toDateTime self.equity data date, so we can format it. Then we can do the implied volatility is going to be the close. So we'll set the index to be the date. So this is a pandas data frame now. We have a column for date. We have a column for close. The close is going to contain the implied volatility data. The date is what we want to index the implied volatility data by. So we'll say self.equity_data.setIndex, and we'll set this to date. In place is equal to true. That means we're impacting the actual data frame itself. We're not creating a copy, or we're not applying this to some sort of copy of that object. We're applying it to that object itself. The implied volatility data is going to be equal to the close, self.equitydata.close. And we can log now using our logger that we have received, and we can plot how much data we've received, the length of the equity data, and then we could say implied vol points for symbol, whatever symbol we got. And then we can also log the date range, and this will be self.equitydata.index.min. And remember, we're using the pandas date time object. That's what we did with the toDateTime. So we can use .min, and this is going to go all the way to the index.max. Okay, nothing too surprising there, just stuff that we would want to see in the console about the data that we received. And a good note that all IVol values are annualized. Definitely worth noting. Now we're going to go about processing this implied volatility data. We want to run these regressions, right? We want to be able to create these. We want to be able to create these this time series of implied volatility. We want to look at the percentiles. So we need a function to be able to do that. We're going to create a function called process implied volatility. And then we're going to create a button, analyze. And now, well, actually, we already have the button. So all we're doing is modifying the state rather. State is normal. Okay, so remember, we're going to leave the analyze button disabled until we are certain we receive data. Here, we're certain we receive data because if 1 is in the historical data dictionary as a key, then that means the server responded with the data for that particular request. So we can go about enabling this button to analyze the data we received. Cool. On the flip side, else, that means the length of data is not greater than 0. No IVol data. No IVol data received. That's a problem. Set the equity data to none. We don't have anything. Okay. On the outer if statement, right, this is just that no implied volatility data has been received. So we can just make a note that and this could be, may not be available for symbol. Worth noting, self.equity data is equal to none. So perhaps it's unavailable for the symbol. Perhaps you're not subscribed to the market data subscription with Interactive Brokers that you need. It's like most of their data subscriptions are like $1. So, you know, whatever it is, we can just make note that there's some sort of reason why the server is not responding with data, because we didn't find the key in this historical data dictionary. If we don't find that key, that means the server didn't respond with data for the symbol. So that's what this note is for. It's roughly equivalent to this note, so we really don't need this, I suppose, here, because if this is true, well, actually, that's not necessarily the case. It might just respond with 0 data. It could respond with the key 1 with no data. So both is fine. Something I just noticed is we created some of these functions within the setup UI function, but we can fix it by just tabbing back out the function itself. So if I scroll up to, let's say, this log message function, I'm just going to highlight it and hit Shift Tab, and it's going to change the color of the function to being used. And that's because this was tabbed in and it was local to the setup UI. We want it to be accessible via the class. So I'm just going to do the same thing for the connect IB and disconnect and query data, and then Shift Tab, and that will make all of these function as intended. Sorry about that. It looks like I forgot to just back out of the setup UI function. So Shift Tab on the log message, connect IB, disconnect IB, and the query data, and we'll be all set to create the next function. And that next function is going to be a function to process the implied volatility. So I'll say def process implied volatility. Self, we will say if there is no equity data, then we can return. We don't need to do anything. Otherwise, let's tell the user that we are going to process the IVol data. Okay. Worth noting that all IVol data is annualized. Okay. Now, keep in mind, we're working with this equity data pandas data frame. The index is the date. We have this column of implied vol, and the server returned the IVol in the close column. So what we want to do is we want to scale that close column by the vol annualization. You could say this is a redundancy because here we assigned the implied vol to the close. So we actually have two columns. We have this close column of IVols and we have this implied vol column of IVols. But tomato, tomato, it's really however you want to do it. So I'm just going to scale that close and store it in this implied vol column. So this is equal to self.equity data close. And then I will square this by np.square root self.vol annualization. Remember, we're dealing with volatility. If we want to scale it to the appropriate time, then we need to use the square root. It looks like I haven't actually imported NumPy. I guess I forgot to at the top, so I'll do that. Scroll all the way up to the top. Import NumPy as NP. Allow us to access some necessary functions like this square root function. So now we can scale it by self.vol annualization. And if you recall, vol annualization at the top here was 252. And we requested, if you go back down to our data requests, daily bar sizes. So we're scaling it correctly. Now we need to create this percentile breakdown. Self.equity data. We will do an IV percentile. We'll set this equal to self.equity data implied vol. Remember, this is annualized. We'll do a rolling window of 252, and we will rank it to percentile. The current implied volatility is just going to be the latest vol point or the last vol point in that pandas data frame. So we can say current implied volatility is equal to self.equity data or we got to get the implied volatility column. And we will say .iloc -1. Remember, if you have a list slice notation, you can go all the way to the end with -1. 0 is going to be the first element. This, of course, is if the length of the equity data is in fact greater than 0. Otherwise, we got nothing. We can get a copy of the volatility data itself by simply making a copy of the data frame for the implied vol and the implied vol percentile that we just came up with, .copy. And now we're going to have to update the display. So we will call a function, update current vol display, that we will create in a moment. So I will say self.update current vol display. We'll create that in a moment based on this percentile and implied volatility annualization. Update the display. And of course, if the self.current implied volatility is not none, then we can log that we have, the implied volatility from the server. And that is that the current ivol is given by, and we can say self.current implied volatility, and then make that a 0.4 float. Then we can do in terms of percentage as well, if we would like to. And this will be self.current implied vol times 100.2f. And then we can add a percent symbol at the end of it to make it percentage. So rounded to 2 versus rounded to 4. That's what 0.4f and 0.2f is in this formatted log statement. Then we'll just give the IV range, and this is going to be the min-max of the time series of implied volatilities. Self.log message, we will say f IV range, and we'll just give it as this range of the implied volatility column, get the max and min. So .min, we'll round it to 4. And we will say dash, not minus, this is the range. So dash, and we'll do the same thing. I'm just going to copy and paste. And we will make this a max. Cool. Otherwise, if the current implied volatility is none, failed to process ivol data. Okay, so we've sufficiently logged everything there. That is our function to process the implied volatility. Now we need a function to update the plot. Or not update the plot quite yet. We want to update the frame with the volatility information that we just queried. So we have this current implied vol data now. We have this time series of implied volatilities. We have that frame with the readout. So let's update everything. So def update current vol display. We will say if self dot current implied vol is not none, then let's update everything. Self dot current vol label dot config. Let's set the text. This will be a formatted string. We have self dot current implied vol, and this will be rounded to 4 places, and of course in percentages this can be we can just quote it in percent. Let's just quote it in percent. We don't need 2 times 100. Self dot current implied vol times 100 to 2. Decimal places float. Cool. So we'll quote it in terms of a percentage. So our current implied volatility there is annualized. Now we're going to do the computation text. So the computation text is equal to annualized by root 252 factor. Important to note what ivol you're working with. So we will do self dot vol computation label, and this will be dot config, and we will make this the text computation text. Equivalently, you could just throw this string in here. Same thing. Then we want to update the vol range itself on the frame. So again, assuming that we have data, we really want to try to, handle all of the edge cases that we might be missing data, and then trying to process the data in all of these functions for the frame or for analysis or regression, whatever it is. So I'm always going to try to handle the data with this is not none. The min is going to be self.equity data. We will make implied vol dot min, and this just makes sense, right? This is going to be the min, the max, the mean. This is for that percentile analysis. Vol max, vol mean, these are just basic calls to the Panda data frame. This is a series object. This is a Panda series, and all of these functions are baked in: min, max, mean. It's quite simple. Then we could do the range text, and we can just set it to vol min. Can round to whatever we want. I'll do 3. Then we could say the mean is vol mean. 0.3 is sufficient. It's whatever you like. We'll do vol max 0.3f. Good. This is going to be in decimals. You can make this in terms of percentages too by just doing what we did here, scaling it by 100 and then rounding to 2 instead. It's however you'd like to do it. I'll do it in terms of decimals here, but if you'd like to do it in terms of percentages, you can just apply that simple scale. Of course, if we have the equity data is none, then this is just going to be NA. Okay. And now we can, since we've handled this range text, that's essentially what this statement was for, we can use it here in the vol range label, and we can just configure the text to be this range text. So that's what this conditional was for. We've configured the text based on the data we've received in the equity data frame. This is a pandas data frame. This is a series object itself when we reference a column, and we constructed this text that contained the min, the mean, the max. We'll throw that in the label so that we can see it. Now let's create some sort of conditional based on the level. So we can just kind of, this isn't really like This isn't static, and it's not really useful because everything is relative to the vol for a particular ticker. But as a baseline and something to make it a little more kind of like systematic, interactive, whatever you want to call it, we can just color the label based on if it's like high vol, like mid vol, or low vol. So we'll just say if the current implied volatility is, let's say, greater than 0.4, then we'll set the label. So the current, I guess this is the current vol label. I want to make sure that I'm using the correct self.current vol label. Current vol label. Yeah. Vol computation label is for the, scaling factor. Okay, so this is based on the current implied volatility. Yeah, current implied volatility, self.current vol label. We are going to configure the foreground to be red. So high vol, red. Elif self.current implied vol is less than 0.15, then we have low vol, self.current vol label dot config. We'll make this, let's say, green. Otherwise, let's just make it, we'll just make it black. Okay. This is just to add some interaction between the UI element that is displaying the implied volatility, the current implied volatility, along with some sort of level. This probably should be based on the percentiles. We have them, right? We can compute them because we have them in this equity data. That is something good for you to try at home. So, I mean, I could leave this as a comment, like, try yourself. Don't use AI. try yourself. Make this based on percentiles. Call it the 25th and the 75th. It's a good exercise. It's pretty easy to do too, because it'll just be baked into these series functions anyway. Cool. And now we're going to call a separate function at the bottom of this to update the regime analysis. And we're going to have to create that next. Update the regime analysis. And of course, if the current implied volatility is none, we'll have this else. We got to set everything to unavailable. So self.current vol label.config. We will set the text to not available. Make the foreground color black in case we changed it prior. Vol computation label.config. The text will be no data. The vol range label, we will say .config. Text will put not available. Self.regime label, not available. Just gonna copy this. Self.percentile label, not available. Self.reversion label, not available. And that should be just about everything we need to update if we didn't get any implied volatility data. So that's going to be our update current vol display function. Now we need a function to update the regime analysis to analyze high vol, above average, normal, below average, and low vol. This is going to be programmed statically, but again, another really good try it yourself is to do this based on percentiles. In fact, this is nowhere near some sort of like math textbook that is, hey, you know, the proof is left as an exercise to the reader. That's just cruel. This is very easy. You can literally just access these percentiles in this series object, and then you can change the color based on them. Same thing with the volatility regime analysis we're about to produce. You could do the exact same thing because we're about to build this function. Just use those series objects. So That's just about as close as I can get to telling you how to do it without doing it for you. So please give that a shot if you want to make this dynamic relative to the equity that you're working with. This is otherwise going to be fixed, and 0.4 might not be high vol. Something like NVIDIA has what? A mean vol of 0.4. So that's not really what we're working with. So definitely try that on your own within this system. Let's create this regime analysis, update regime analysis function now. We're just kind of iteratively going through building out all of the components of this UI based on the data we receive from the server, the implied volatility data we receive from the server, and very soon we're going to be going about constructing the actual regression itself. So let's build this function to update the regime analysis. This is going to have fixed values based on the percentile. So essentially it's doing what I'm suggesting here for this guy, but the percentiles themselves are fixed. 0.8, 0.6, 0.4, 0.2. You can come up with your own methodology if you'd like to use different percentiles, but you know that's completely up to you. So for now, let's start by creating this update regime analysis function. Def update regime analysis self. Here, if we don't have any vol data, or the current implied volatility is none, then what happened? We don't have any data, so there's nothing to update. Return. Otherwise, the current percentile is equal to self.vol data. Remember, we created that copy. We have this vol IV percentile. We want to get the most current, so we'll use -1. And now we can determine the regime. So this is going to be static. You can make this dynamic however you want to do it. But I'm going to say if the current percentile is greater than 0.8, I will define the regime as high I vol. I will say the color is equal to red. If the percentile is greater than 0.6, I will say the regime is above average. I guess we don't need eyeball. I'll just call it high. Nah, we want to keep it in terms of eyeball to make sure that it's clear we're working with implied volatility. There's no approximation of realized volatility here. We're dealing with historic implied volatility. So regime above average eyeball. The color, we can call this just maybe like orange. Okay. Elif. Current percentile is above 0.4. We will just call this normal. Return. We'll just make this black then, if it's normal. Current percentile is greater than 0.2. This can be considered below average. Regime is equal to below average eyeball. Maybe make this blue. Otherwise, this is just low. And the color can be green. Okay, this is just some way to rank the current status of implied volatility. It's worth noting that like these aren't mutually exclusive, right? Like you can be over 0.2 and over 0.4 and over 0.6 and over 0.8, right? 0.9 satisfies everything, but I mean, this is just like basic programming. I think it's just worth noting the difference. You know, if, elif, 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 we're dropping through each of the conditionals here. Definitely worth noting for if you're unfamiliar with the Boolean logic of how this functions. All of them can be true, but if this one's not true, then we'll check for this one and so on and so forth. But that's why we're not, you know, automatically triggering all of these along with this one, right? Okay. Let's configure the regime label now. Now that we have this regime in color, we can configure the regime label. So the label itself, right, we can config, we can set the text to be this regime. The foreground, we'll set it to this regime color that we called color. And the percentile label, We have that based on the percentile, the current percentile. That's what we used to compare to these fixed values. So the text will be equal to this formatted string, the current percentile, and we can just round to 0.1%. Cool. Can talk about some sort of reversion expectation too. This is the idea that volatility is mean reverting. That is something that we observe within the market. We see that volatility is a mean reverting process. The mean itself, non-stationary, it's not a fixed value, it can oscillate, can change over time. But something to keep in mind is that we can expect some sort of reversion down or up to some sort of mean. Not crazy to think if we're above the 80th percentile that on average we're going to see some sort of reversion to a mean down. Same thing with reversion up below, say, the 20th percentile. So if the current percentile is greater than 0.8, this could suggest some sort of reversion down. So expect mean reversion down. And the color for this, we'll call this R color for reversion color. We'll make this blue. If the current percentile is less than 0.2, then we can do the same thing, but it's going to be mean reversion up. And the color is going to be black. Oh, good. It didn't get cut off. I was concerned. Good. Okay. It's in between. You know, really, we don't have any sort of reversion. So this is going to be like a neutral, quote unquote, signal. And we'll call this R color just black. Okay. Then we can update this reversion label to be the reversion text. And the foreground color will just be the R color. That is the color of the reversion up, reversion down, blue, black, or black. I guess instead of black, it should be red or green. I think we could leave it as red. If it's low vol, then expecting a reversion up implies that volatility is going to increase. Color red is probably fine for that. Maybe orange, but however you wanna do it. Okay, and that should be sufficient for this. Yeah, that's going to be sufficient for this update regime analysis. Now we can move on to actually analyzing the volatility itself. This is where we're going to build out the data frame for the regression analysis. This is where we're going to take the average forward 30-day implied volatility. So it's a forward-looking average of implied volatility from the current point in time. We're doing this on a rolling basis. We query back 2 years of data, and all the way back, we're going to pretend that's the current point in time. We're going to look ahead 30 days, take the average implied volatility, and we're going to regress that on the current volatility, the current implied volatility at that point in time. And we're just going to keep doing that rolling forward. There's a lot of ways to improve this methodology. You could do this in a disjoint capacity. You could do this for particular clusters of volatility. If you're starting high or starting low, there's a lot of ways to condition this, improve this regression. But again, this is a very involved video building this from scratch. We'll focus on the code, focus on this implementation. Perhaps in another video, we'll talk about ways to improve it, talk about using this maybe for live trading. But again, you know, this is a very involved technical video, so please let me know if that's something you'd like to see in a later video. You've already been a trooper, you've made it this far, and now is really time for the bread and butter of this video, and that is building this function to analyze the implied volatility. Okay. I would also like to do a more involved video on regression eventually. You know, this idea of a geometric interpretation, a projection, this idea of how we actually get to the equation for it, the difference between, say, like a multiple regression or just a single variable regression. There's a lot I'd like to discuss, but everything is largely based on interest. So let me know if that's something you'd like to see. Nevertheless, let's get started here. We'll analyze volatility. It's worth noting all of these functions are already implemented in our user interface. So we built out, say, the query data function. We call that function as a command from the query button. It's already built. Same thing with the analyze button. This analyze volatility function is what we are calling, and that's what we're building right now. So don't lose sight of this. We have this user interface. We have all these little frames. We're building this functionality out. If we don't have any data, can't do anything. We can show an error that no IVOL data is available for analysis, and we'll return. Okay. Otherwise, let's log that we are going to be analyzing the implied volatility data. Let's get this data frame of the forward 30-day implied volatility. We'll get this from the volatility data, the implied volatility. We're going to compute this on a rolling basis. We're going to do a window of 30 days. Minimum period 1. Take a mean and shift it 30 days. Okay. Then what we're going to do is we are going to create this analysis data frame that's going to keep the current vol, the forward vol, the vol difference, and the vol percentile. Okay, so let us do this. The analysis data frame is going to contain the current vol, self.vol. This is just going to be the implied volatility data, the forward vol that we just created, the forward 30-day vol, the difference. Remember, this is for the different regimes. And then the percentile. Cool. We'll drop all NA values because remember, we're shifting the future values to match up with the current values. That's how we're doing this regression. We're regressing the future data on the current data. And we're seeing if there's any explanatory power in the outcome, the average IVOL for the next 30 days. So we'll do analysis df is equal to analysis df.drop NA. You could just drop in place that is equivalent to this, but we'll just use this for now. This is equivalent to analysis .drop NA in place true. So use whichever you want, but in place just means it's operating on that particular object, and it looks like this to act on the particular object. Worth noting, we can also note if we have insufficient data for analysis. So if the analysis data frame is less than 30, we don't even have a point to regress. So we can just log that we have insufficient data. And in that case, we'll just return. There's nothing else to do. Otherwise, it's time to do some regressions. So we can import SciPy here. Guess I forgot to at the top. So from SciPy, import stats. We can do slope 1, intercept 1, R value 1, P value 1, standard error 1. Is equal to stats dot lin regress, and here we're going to do analysis data frame current vol is equal to some intercept times a slope of analysis df, and we will have the forward 30-day vol regressing the forward 30-day vol on the current vol. And we're going to do this as well for the difference. So I'm just going to copy and paste it as slope 2. Slope 2, slope 2, slope 2. So slope, intercept, R value, P value, standard error 2. Current vol, not on forward, but this time we're going to do it on vol difference. Okay. We're going to look for this split point between y equals x. And that's really just a system of equations that we're solving to find that breakpoint. Remember, we have this low vol regime and high vol regime. And solving that system of equations is going to give us the breakpoint. So if slope 1 is not equal to 1, then we can find this breakpoint. If it's equal to 1, then it's equal to that dotted line, y equals x. And, you know, there's not going to be a breakpoint. So the intersection will then occur at, if you solve the system of equations, intercept 1 divided by 1 minus slope 1. Okay, quite simple. Otherwise, the intersection x is going to occur not at all, so we'll just use the median. That's the middle value. So to separate the low and high vol regimes, we're going to look for that intersection between the regression line and y equals x. That is, if the forward 30-day I vol actually matches what the current I vol is, then we will just take the median. If the slope is equal to 1. All right, let's create this high vol regime and low vol regime. This is very simple. All we're going to do is apply a filter to the current vol in the analysis data frame, and it's going to be based on this intersection point. So the high vol regime is going to create points for analysis. It's going to create points for analysis based on the current vol if it is greater than the intersection x. The low vol regime is going to be the complement. Less than or equal to intersection x. Perfect. And now we can just run these regressions separately. So if, let's say, high vol regime dot sum is greater than 10, we can run this regression. That's just a conditional to run this regression. So let's just copy this regression code that we had up here, and we will run it within this if statement. And instead of slope 2, we'll just call this slope high, and we'll do intercept high, and we'll do R value. We'll just call it R high. We'll call this P high, and we'll call this standard error high. The actual regression itself is going to be done based on this filter. The high vol regime is going to return, so this filter itself, right? This is going to return a series of booleans. And wherever this condition is true, it's going to be 1, otherwise it's going to be 0. So we will base this regression then off of the analysis df, but we're going to find places where what? The high vol regime applies. Same thing for the difference, where the high vol regime applies. So it's going to be dot loc, and we're going to find those places where the filter applies. If we have insufficient data, then we can just set all of these equal to each other and none. So we will set this equal to none. Say these are all equal. Wonderful. So that is for the high vol regime, and we're just going to replicate that for the low vol regime. So we'll copy this, do the exact same thing. And instead of high, it's going to be low. So call this low, low. It take 2 seconds to do a search replace, but I'm dedicated now. Standard error low, good. Copy this, make all of these equivalent to none, if we have insufficient data. Cool. This is now the low vol regime, not the high vol regime. Same thing for these filters. We're going to be applying the low vol regime, not the high vol regime. Same thing, it's going to return a series of booleans based on this intersection, and we want to find all of the points where it's true that it is in fact a low vol regime. And remember, that regime is based on the intersection between the line y equals x and the regression line that we came up with in the unconditional regressions. So that is exactly how we're going to be doing this. I think now we're ready to plot everything. So we can do x1 clear, x2 clear, x3 clear, and then we can create this this scatter plot of data and then plot the regression line. So what does that look like? Well, we're going to do self x1.scatter. This is going to be a scatter plot, and we're going to plot what? All of the current implied volatility points against the forward 30-day volatility points. To make this look a little nicer, we can set the alpha equal to 0.6 and the size to say 20. Let's add the regression line to that plot. So the x range is going to be mp_lin space. We will go from the min of the current implied volatility available all the way to the max of the current implied volatility available. And then we will do 100 points. Remember, any function that you're plotting is going to be some sort of linear interpolation. It's just like really small lines that are being connected. We can't really plot like a true continuous function. Can't have a point that's infinitesimally small. You know, that's just getting into the weeds though. So let's talk about ypred1. This is going to be the output of the regression equation. So what is this first chart? This first chart is the unconditional regression. That is the regression of what? Forward vol on current vol. We got that from here. So we want to use the slope and intercept to construct the equation of the regression. So we will do slope 1 times this input range, this is the domain, plus the intercept 1. And then we can plot it by self.x1.plot x range. We're going to plot the regression line, and we will just make this red, line width. Line width is equal to 2. And for a label, we'll just call this some sort of formatted string. We'll say regression r squared is equal to, and we'll put the r value 1. We can square it, and then this will be rounded to say three places. And that's going to be our first plot of data. So this is the unconditional regression of forward vol on current vol. And we're going to do something very similar for the difference. But don't forget, we still want to plot the y equals x line as a reference. So we'll create this min val, set it equal to the min of the current vol and the forward vol. This can be seen maybe as a little redundant because, you know, if it was not disjoint, then there's no way for the average to be lower than any one of the points. I mean, that's just like sort of a basic math thing. Like if you have, let's say 10 points and the lowest is 1, like let's say you just have an ordered list 1 through 10, then the average can't be lower than 1. So you could look at this as redundant, but if it is disjoint, then you may actually have that as the case. So we'll create this min val. Max val is equal to max. Same thing. We'll look at the max between the current vol and the forward I vol, and we'll take the max. Oh, I didn't take the max over here. Cool. And now I'm just going to plot this as y equals x. So I'll have the min val, max val, and then the min val, max val. And that's just going to be a line. So we'll do k, we'll keep it dashed. We'll do a smaller line width. And we'll just set the alpha to 0.7. And then the label will be y is equal to x. So this is no change. That's the point of this line. It's a reference. If the forward 30-day implied volatility is equivalent to the current implied volatility, then there's no change observed on that, the average 30 days going forward on average. All right. Now we're ready to look at the, well, I guess we could set the titles. So we'll set the X label to be the current implied volatility. The Y label will be the 30-day forward average implied volatility. The title will be the forward implied volatility versus the current implied volatility. We could plot the regression equation too as y is equal to, we have slope 1. We can round to say 0.3f, and we can also throw in the r squared. We'll have the intercept too, of course. So intercept, good. Maybe we'll just put that after conventionally. Plus the intercept. And we can also plot the r squared, which is just going to be the r value squared, r value 1 squared, and we can round that to 0.3f. Sufficient. Add a legend to that plot too. And then create a grid with some alpha. Try to make it look a little nicer. And that's going to be the first plot. So that's the unconditional regression of forward vol on current vol. Now we want to work on the second plot of the difference. So what we'll do is we'll do pretty much the same thing, but we're going to create a scatter with a color label for high and low volatility regimes. So now we're working on the second chart. So we'll do self.ax2.scatter. We'll do analysis data frame. We will do the high vol regime, and we will make this the current vol. And we want to also look at the vol difference. We have to locate this. So remember, we're just applying these filters here. This is nothing crazy. So for this scatter, what we're doing is we're looking at the current vol and the vol difference only in the high vol regime right now. That's exactly what we did with the regression up here. So it's the exact same idea. Okay. So we'll come back down here, and what we're going to do is we're going to apply some style to the chart. So alpha is equal to 0.6. The size will be, let's say, 20. Color is red. Label, we will say, is high vol regime. Okay. We will say analysis data frame, locate. This is the exact same thing, but we want to use low vol. So I'll just copy this, paste this. We will use the low vol regime filter now. Remember, this is a series of booleans, and we are looking for data, the current vol and the vol difference, where we are in the low vol regime. Okay, so keep in mind the objects that we're working with here. This is a data frame, and we're applying a series of booleans as a filter, locating where what current vol and vol difference fall into this particular regime. You can also do it with if you just query the column directly and then pass this through through brackets afterwards. So that's another way of doing it. But even still, this is not a high vol regime anymore. This is a low vol regime. Instead of red, this should be blue or green or whatever you want to do. Okay. Now we're going to add the appropriate labels based on the regime. So if the slope is not none, that means that the regression equation is valid. It's not zero. We didn't have an issue computing the regression. Essentially, the regression functioned, and we have some sort of slope. We could say x high is equal to analysis dot loc. Again, we're operating in this high vol regime. We want to find the current vol. If the length of x high is greater than 0, then we need to create this range x high dot min to x high dot max. 100 points. This is exactly what we did earlier. YPred for the high vol regime. This is constructing that regression equation. We have slope high times this input domain x range high plus this intercept high. So this is our regression equation. This is our domain. This is our range. Now we can plot it. Self.ax2.plot x range high y pred high, and we can do make it in red for the high vol, line width equal to 2. For the label, we'll just do a formatted string. We'll say that this is the high vol with an r squared of, and then we will do the r squared from the regression. We will round it to 3 places. Cool. That should be correct for the high vol regression. Let's do the same for the low vol regression. So if slope low is not none, then x low is going to be based on this low vol regime. Then we will use x low dot min, x low dot max for the range. This will be x range low, y pred low. This is gonna have to be slope low. This is gonna be x range low. This will be intercept low. Okay, and then we're gonna be using y pred low, x range low, and this is gonna be now low vol. So what we've just done is we've plotted on the same subplot. So this is axis ax2, right? So we have plot 1, plot 2, plot 3. Plot 1 is the unconditional regression. Plot 2 is the conditional regression based on the volatility regime that we solved that system of equations for y equals x and the regression line. That intersection creates 2 buckets. Now we're going to be plotting both of those points separately, and we're doing that by using this filter that we created, the high vol filter and the low vol filter that we constructed up here. Okay. Easy enough. Now we can actually just plot everything. So, or not plot everything. We can just label everything. So self.ax2.axh line, y is equal to 0. Color is equal to, okay. Line style is equal to dashed. Line width is equal to 1. Alpha is equal to 0.7. Label is equal to no change. Y is equal to 0. This is a difference, right? We're regressing the difference on the current vol. The point of intersection between the unconditional regression and the y equals x line is now differenced, and its origin is going to be y equals 0. Okay, so that's where this h line is coming in, and we are going to use this essentially as like, okay, there's no change between the current vol and the current vol and the forward realized vol. So let's say the current vol is 0.3. If the forward vol is also 0.3, then this would yield 0. That's what this h line is, this horizontal line. The vertical line is the intersection between y equals x and the unconditional regression line. I might have just swapped the two actually by accident when I was just talking. So this x horizontal line, or this line at y equals 0, is what occurs when the forward vol is the same as the current vol. Now we're going to look at the vertical line based on the unconditional regression and y equals x. That is going to be this vertical line that's breaking up the two sections into a low vol regime and a high vol regime. That's this vertical line. This is this V line, and this is going to be at the intersection x. That's what we solved for the two regimes. We have, let's make this green. Line style, we'll make this kind of dotted. Line width will be 1. Alpha will be 0.7. And this is the regime split. So the label for this, I'll just make this regime split. And this will be at vol is equal to the intersection x formatted. We'll round that a bit. Cool, so that's going to help our ability to interpret this difference regression. Now we can just set the axis labels themselves. So the title is, or the x-axis is going to be the current implied volatility. We're regressing the difference on the current implied volatility. It's forward minus current, okay? So if current is very high, call it 0.7, and forward is lower, call it 0.3, then this will be negative. That implies that forward realized vol is going to be less. Negative, less. Positive, more. It's quite easy to interpret. So now we can set the title. Vol difference versus current vol. This is a regime analysis. Cool. Add a legend. Legendary. Cool. Ax2.grid. Sure. A little bit of alpha there. Okay. Good. That is it for plot 2. So that is the regression for the unconditional regression and the conditional regression. Now let us put together this time series of implied volatilities with the percentiles. So we will essentially be creating in this third plot the time series of implied volatility that we queried back to for, along with the 75th and 25th percentile to see where current implied volatility is relative to where it has been and maybe where we can expect it to go in the future. Fortunately for us, this last plot is actually quite easy relative to the two regression plots. It's just a time series plot with some percentiles. So we can access that third axis, Ax3. And what we're going to do is we are going to plot simply just the implied volatility data. So we're actually going to get that from the volatility data frame. We will get the index as the x value, because the index is just going to be the time, and we're going to plot the corresponding implied volatility. Cool. This is just going to be the label is implied volatility. That's all we're plotting. It's just a time series of implied volatility, and the line width can be 1. Fantastic. The percentile breakdown, we're going to plot horizontal lines for this percentile breakdown. 75th is equal to, again, this is just going to be accessing it from the data frame. And we can access the quantile from the series object. Actually, this is exactly how you do what I said to try at home right here. So, you know, you just got to substitute these if statements in for these guys here, and you will you'll have a dynamic way to quote high, mid, low, low vol in that sense. So vol 75th, cool. Vol 25th, cool. You can do whatever you like here. I'm just going to use 75th and 25th. We'll do implied vol. We'll do a quantile 0.25. Good. Then we want to plot these. So what I'll do is I'll do ax3.axh line. Y is equal to vol 75th. Color is equal to red. So this is when vol is getting particularly high, right? So line style is equal to, we'll do dashed. And then alpha is equal to 0.7. Label, this is just going to be the 75th percentile. Then I can just do the same thing for the 25th percentile. We can make this green. Again, it depends on how you look at it. Could be that when it gets to the 25th percentile, it's going to revert. So vol is actually going to go up. Can make that red. Dealer's choice. I'm going to make it green. 25. Cool. And then we will have another line for the mean. So I'm just going to actually do the same thing. But the Y is going to be based on the mean of implied volatility. Self.vol_data. Get the implied volatility dot mean. Instead of red, this will be black. And instead of 75th percentile, we will do the mean, the average. Fantastic. Okay, and now we can just go ahead and plot the current point and then set the axis titles, set the labels. So if self.current implied volatility is not none, so we have data there, we can just scatter plot this data as just the 1 point. And that's just going to plot this 1 point. So we will just get the time to be the latest time that we have data for by doing index -1. Then we will do self.current implied volatility. And this can be just a red point. Maybe make it blue to make it look a little nicer. We'll just leave it as red. It's fine. You can also condition it if you wanted to make it like high, low, medium. It could be something cool to add. 100 Z order 5. That's going to bring it up on top of all of the other chart elements. And then label. This is the current eyeball. Cool. And then we can do self.ax3.set x label. This is going to be the date. Self.ax3.set y label. This is the implied volatility. Again, this is just a simple time series. It's pretty easy. It's just a time series with percentiles and the mean. Again, not non-converging values, right? These are time variant values. The period that you query for is going to change the mean. So it's an expected level. I go on about this in a lot of my videos. The expectation doesn't exist in the classical sense of a random variable converging. This is a time variant distribution, something to keep in mind. This is a very important idea that I talk about all the time, but even still, the model is wrong, the expectation is wrong, these expected levels are wrong, the percentiles are wrong, but that does not preclude us from making money, right? If we know that vol is particularly low, then yes, it's going to come back to some sort of mean value. If vol is particularly high, it's going to come back towards some mean value. So again, these values are wrong, doesn't preclude us from making money. ax3.set title. We're going to make this implied volatility time series with regime bands. And in this case, the regime is not the intersection between the y equals x line and the regression line. It's just going to be based on this idea of 0.75 and 0.25, these percentiles. Don't get those two mixed up. They are, in fact, different high and low regimes in that sense. Okay, we can add a legend. Cool. And we can add a grid. Fantastic. And what we actually want to do too is we're going to want to rotate the dates because they're going to overlap. So we'll do tick params. The x-axis, we will say there's a rotation of 45 degrees. This will ensure that dates don't stack on top of each other. We're almost done. All we have to do now is draw these canvases and then create an instance of this implied volatility dashboard class, and we'll be ready to test this app. Now, another thing we can do is log all of the results of the regressions and even log conditionally logic to suggest, hey, expect mean reversion up, expect mean reversion down. I'll include this in the source code on GitHub, along with this version that we've built together in this video. But I certainly encourage you to do that analysis on your own. It would take me a significant amount of time to just type out all those conditional statements. So you can check out the source code on the complete product if you want to see the type of analysis you can do with the regressions. That is, where is their edge, where is their expectation of reversion up, reversion down. But I certainly encourage you to try to create those rule sets yourself based on these regressions. Nevertheless, what we'll do now is we will set a tight layout for these figures, and we will go ahead and draw them. And that's going to do it. It's going to do it for our figures. And that's going to do it for the implied volatility dashboard class. So we're ready now to create this, this load function. So we'll call it main. And in here, I'm going to create a root, tk.tk. And just like we said earlier, we're going to have this app, this implied volatility trading dashboard. We'll pass this root to it. And that's why we were able to use self dot, accessing everything within the main frame of our application as we built it out. And we can just run this main loop, and that is the loop to keep the frame up for the life of the application. And now if name is equal to main, we will run this main function. Fantastic. Moment of truth here. I'm sure something is broken somewhere. It looks like column config. So object tk app has no attribute column config. I think that should be column configure. That's on line 70 something, 75. So let's scroll on up to line 75. This is all the way at the start here in the setup UI function. And yes, we call column config, should be column configure. Column configure. Okay. Let's give this another shot. Let's see if we can run this. There we go. All right. So this app just launched here. And now we're ready to try to run a connection to the trader workstation on Interactive Brokers. So I'm going to open up Interactive Brokers and show you where to go to configure your ports and establish this connection. All right, so once you open up Trader Workstation, let's say you logged in, you click on the little gear icon in the upper right hand corner, you open up this settings window, you're going to head on over to API, settings, enable ActiveX and socket clients, and this is where you can set your socket port. This is also where you can set your master API client ID. That is the third parameter we talked about, that 0 parameter with multiple client IDs and such. So something to keep in mind. You can also enable read only so that you can't execute trades. You have other precautions here if you would like to bypass order precautions and such and such. So a lot to work with, but enable ActiveX and socket clients, and there is your socket port. So if you want to change your socket port, maybe you're running Minecraft on another port. So maybe you need to run this on 7498. Who knows? So you can change that here, apply, okay, and then we will be ready to run a connection from our client that we just built. All right, I'm back on the Implied Volatility dashboard. I'm gonna run it, and I'm gonna try to make a connection request. It looks like we have some sort of error because it's not breaking that for loop. Connection error, string object cannot be interpreted as an integer. This is probably something with our host and port. So I'm going to close out of this. You have a main loop in your applet. So if you can't run this again, what you'll have to do is come to this terminal, either delete it or Control C to break out of the loop. Just something to keep in mind as you try to test this application. So we had an error with our connection. I'm going to scroll on up to the connection, and lo and behold, it looks like we have a little bit of an issue here. The port needs to be an integer when passed to the connect function. So I'm going to make this int. I'm going to cast this string to an integer, and that should fix the issue. So far what we've done is we've fixed the configure in the frame, and we've fixed this this port being accessed as a string. So we're going to access it as an integer instead for this connect function here. Let's go ahead and try to run this again through this debugging process here. Let's connect. It looks like we are actually getting a valid connection to TWS, but we still fail to connect effectively. So if you look at the terminal here, we do have a successful connection, but what's happening, it would appear, is we are never triggering the flag that we've been connected. And it looks like this is because we never actually implemented the next valid ID. We've never told the client that we've been connected to the server. So what I'm going to do is I'm going to go into the IB app wrapper, and I'm going to create a new callback function. And this callback function is called next valid ID. It looks like it implemented it for me. Essentially what it's doing is once we connect to the server, it's going to respond with an order ID that's valid if I wanted to execute some sort of order or trade. But I'm going to use this as an acknowledgement that I've connected to the server. So I'll just say connected is equal to true, and I can print connected to IBTWS. Okay, so I'm going to close out of that last run. Going to give this a shot here. We'll run it again, see if we can connect. I'll hit connect, and looks like we've successfully connected to IBTWS. If I look at my console, we have successfully connected. So we have successfully connected to the creator workstation, and now we can try to query some data and see if our regressions work. What I'm going to do to test this query function is I'm going to use SPY in a 2-year duration. I'm sure stuff is going to break, but we will fix it as necessary. So I hit query, and it looks like we're waiting past that 5 seconds. So let's see what could be wrong here. It looks like we are using in eClient rec historic data. We should be using form date, or we're using form date. We should be using format date. So in the rec historical data, this is, remember, if we go back up to our query data function, we have this rec historical data. We should be using format date. And it looks like we should be using chart options too. So we need to add an S here, and this should be format date. Okay, so what I'm going to do now is I'm going to close this application, Control C in the terminal. I'll clear it with clear, run this again, see what we get. Connect, query. Looks like we're getting a different error. If we go back to our terminal, your API version does not support fractional shares. We can actually ignore this rule in the error that's returned. So that's what we're going to do. I will clear this terminal again, and we will go up to the IB app now. And in here, we will do if the error code is equal to 2176, and let's say fractional share is in the error string dot lowercase, then we can just ignore. So we will return and that is sufficient. Another potential issue I just read here is if rec ID is not in self.historical data. Remember, this should be our dictionary for historical data, but we're actually calling this function. So this should be historical data. That should be sufficient now. So that should be all the changes that we need. Famous last words. Let's give it a shot. So we will connect. We will try this again. All right, I'm going to connect. I'm going to query IV data. All right, cool. The first query worked. We got the implied volatility data for 2 years for SPY. This is the current implied volatility, our computation, our scaling factor, the range, the current regime, the percentile, and the mean reversion signal. Let us analyze the implied volatility. Looks like we're having trouble analyzing the implied volatility. We get an error, and that error is text object is not callable. This is on line 450. It looks like we're just calling the title. This should be set title. So let's go to that figure on line 450. This is going to be, here it is. This should be set title. Okay, let's make sure we didn't make that mistake elsewhere. Set title, good. Good. All right, now we can try to give this another shot. And I will try to connect and query again. So connect, query, analyze implied vol. Would you look at that? We have the regressions that we are after. So here we have the unconditional regression. We have then solved this simple linear equation to find the intersection of these two lines. Then we plot that intersection right here as the vertical line, conditioning on the low regime and the high regime. We have two separate regressions, and then we have this time series of implied volatilities with the percentiles, the 75th, 25th, and of course the current vol and the mean. And that is everything that we were after. So we can try this again. Let's say with another one, we'll use NVIDIA. I hit query. 44% implied vol, analyze, and boom, there we go. There is the dashboard and the analysis for NVIDIA. And we have successfully built this implied volatility trading dashboard. Man, oh man, this was a long video. I hope you enjoyed. I hope you learned something. This was a lot of fun to put together. Coding without AI is still super, super important. They go hand in hand. You can write a lot of code with AI very quickly, sure, but somebody has to go in and fix everything. I mean, even at the end of this app, once we started putting all of the pieces of the puzzle together, when we tried to run it, different errors were made at different points in time. We had to go in and fix it. We had to understand what objects we were dealing with. If you were creating some sort of backtest or some sort of system that was paper trading, and you had some errors or you didn't know why the order executed at this price, whatever, you would have to go in and figure out why. So very, very important that you can still code on your own. Very important you can write code without AI. This was a very fun video to create, but this was also a very, very long video, a very difficult video to create. It took a lot of effort. So if you enjoyed, please like, comment, subscribe. It helps me out a lot. Let me know if you want to see videos like this in the future. I love creating how-to videos. So, let me know. We can even, work on using this implied volatility trading dashboard, maybe even generating trades automatically using this implied volatility trading dashboard, all with, of course, interactive brokers and the trader workstation. Let me know what you'd like to see in the future. I have a lot of ideas, a lot of how-tos that I could create. Other than that, please check out quantguild.com if you'd like to support the channel, master your quantitative skills. Other than that, thank you so much for watching, and I will see you in the next video.